Okay, folks, we'll make a start. So we're going to start today by looking at the next part of the nomenclature and isomerism chapter 25 of the A-level course. And we're going to start, like we did last week, with a bit of an AS recap. So we're going to be looking at isomerism in all of its wonderful forms. So start off with, I'd like to have a go at this particular activity here. So a definition of structural isomers, a definition of stereo isomers, and then using C6H12 as an example, could you give a positional isomer, chain isomer, functional group isomer of hex-1-ene, and then give me two geometric isomers that are both C6H12. So basically, fill in that box, and that, and that box using C6H12 as an example. All right, and I'll give you about 5 minutes to get that done. Okay. Morning, Cecil. So again, with these three here, use hex-1-ene as your starting molecule. So a positional isomer, chain isomer, and functional group isomer of hex-1-ene. Here, do whatever you think. Great. 2 more minutes. 2 more minutes. Okay, folks, we'll make a start with going through these answers. So we'll start with the definitions. So the definition of structural isomers, you're looking for compounds or molecules with the same molecular formula, i.e. C6H12, something like that, but different structural formula. So same molecular formula, different structural formula. That's the definition of structural isomers. Stereoisomers have the same structural formula, but different arrangements of atoms in space. Or some of your teachers might say a different 3D arrangement of atoms within the molecule, different spatial arrangement of atoms within the molecule, anything like that will do. But the key thing is that structural isomers have the same molecular formula, different structural formula. Stereoisomers have the same structural formula, but they have different arrangement of atoms in space. All right. So using hexonine as an example, all right, can we give a positional isomer, chain isomer, and functional group isomer of hexonine? All right. Has anyone got any answers? If you just give me the name of the molecule that you think I'm going to be drawing, then I'll draw it. So give me one or two structural positional isomers for hexonine. Don't be shy. Thank you, Mrs. Patel. Perfect. Yeah, we've got hextuine. Hextuine, or, all right, thank you, Steve. Is there another one? Is there potentially hexthreene? Right, could we have the double bond on the third carbon to give us something different? Yeah, I think we can. So we can see that hexonine, hextuine, hexthreene are positional isomers, or hextuine, hexthreene are positional isomers of hexonine. Chain isomers, you've got to be careful with this particular one, because a lot of students make the mistake of when they're doing a chain isomer, they also do a position isomer at the same time. So I know that I just want it to be a chain isomer, to have a different chain length. So I want that to have a different chain length. I'm not going to move the position of the functional group. The functional group is going to stay in exactly the same position. So it's on the first carbon. And then because that's 6 carbons long, I'm going to try thinking, right, can I have a one that's 1, 2, 3, 4, 5 carbons long? Yep, that is a different chain length. And now I can put in my extra carbon, put it as a methyl group somewhere within the molecule. So you could put it there, you could put it there, you could put it there. All right, that's just if you want to have a 5 carbon chain isomer. There are a lot of other ones if you want to go 4 carbons chain isomers as well. So I'll just give you one example. Let's go with the first one here. Can anyone successfully, other than Cecil, name that molecule? So what would we call this molecule here? Two methyl pentoine. Great effort there. Well, let's just figure out whether or not that is correct. So well done for identifying that it is pentoine. That is definitely pentoine. However, Once you've identified it as pent-1ene, you've automatically assigned this as carbon 1, that as carbon 2, and then that must be 3, 4, and 5. And once those numbers are fixed in place, you can't then change them. So I can't just number from this end to name it as pent-1ene and then that end, because the methyl group's closest to the tail, right? So it must be 4 methyl pent-1ene. Just be aware there's no gap between the L and the P. All right. And functional group isomers. So does anyone remember, how do you make a functional group isomer from an alkene? Well, an alkene is a hydrocarbon, so you've got to turn it into a different hydrocarbon. Any answers? Give me a name. A cyclohydrocarbon, yep, well done. Obviously, there are a couple of examples you could have here. Easiest way would just be something like 6 carbons. So if I do, but take out the double bond, all right, so that will become cyclohexane. Yep, there's one example. So you're turning an alkene. The only way to turn an alkene into an alkane is to ring it, to actually put all the carbons into a ring. There are other examples. Again, you can pretty much draw anything as long as it satisfies the laws of bonding, i.e. carbon makes 4 bonds, hydrogen has made 1, and it's got C6H12. So you could do a square, for example, and then 2 methyl groups coming out of it. And like I say, there's loads of different possibilities there. Okay. So these are all structural isomers, which means they are all C6H12 because they've got the same molecular formula, but they've got different structural formula. So let's move on to the geometric isomers then. So correct, so there will not be there are cycloalkanes, there will not be a double bond in that structure. Well done. Geometric isomers then, they've got the same structural formulas but different arrangement of atoms in space. This is the EZ isomerism. You can call it EZ isomerism. Its actual name is geometric. So again, which isomers have you gone with here? Well, I've actually got one just here. Here's one I made earlier. Okay, so you can see that it is 1, 2, 3, 4, 5, 6 carbons in a row. There are still 12 hydrogens, and the double bond is there. All right, so the double bond is on the second carbon. So what would I name this particular molecule using geometric isomerism prefixes? So what would I call this? Z-hex-2ene, we have a final answer, and that is correct. I'm clearly wasted as a chemistry teacher. Should have been some sort of living statue. So it is Z-hex-2ene. How do we know that it's Z? Well, it's hex-2ene because it's 1, 2, 3, 4, 5, 6, 6 carbons, alkene, and the double bond is on the second carbon. And then the 2 priorities on either side of the double bond, that one, because that has a higher atomic number than hydrogen. And on the other side of the double bond, we've got a carbon here, which has an atomic number of 6, and hydrogen, which has an atomic number of 1. So the 2 priorities are both on the same side. They are zusammen, which is German for together. So it is Z-hex-2ene. So if I was drawing that out skeletally, 1, 2, 3, 4, 5, 6. Okay, I've bent it around slightly so you can clearly see it, but that would be Z-hex-2ene. You can also have E-hex-2ene, and E-hex-2ene would be just swapping these over here. So the priorities don't change. So this is the priority on that carbon in the double bond, and this group here, this propyl group, is the priority of that carbon in the double bond. And you can see they're on opposite sides. One's pointing down and one's pointing up. So one's on the opposite side of the molecule. So they'd be entgegen. Which means it looks something like that. All right. So that's E-hex-2ene. And again, classic question comes up all the time, all right, is what prevents what structural feature of an alkene prevents an E isomer from turning into a Z isomer? So here's my Z-hex-2ene. Why can't I just flip this round and get that pointing at the top? Yeah, there is restricted rotation about the double bonds. Double bonds don't rotate very easily. So because of that restricted rotation, I can't twist it. You can't actually get this up to there, which is why it exists as two different molecules. Will that affect the overall chemistry of hex-2ene? No, they've got the same functional group. It's in the same place within the molecule, but it will affect physical properties like boiling points. So the E isomer would probably be able to pack closer together, have stronger van der Waals forces, and a slightly higher boiling point as a result. Okay. So we've looked at all these forms of isomerism. We're now going to look at the new one, all right, the final one that you come across in A-level chemistry, which is optical isomerism. And optical isomerism is a form of stereoisomerism. And don't forget, you never forget your definitions. Stereoisomers, same structural formula, different arrangement of atoms in space. Okay, so let's have a look at, I'm going to do two things. I'm going to show you the structural feature of a molecule, which will tell you whether or not it exhibits optical isomerism. Then I'll tell you how to draw it, and then I'll tell you how to distinguish between them. So let's have a look here. So for something to exhibit optical isomerism, it must have a chiral carbon. Yeah, so there must be a chiral carbon. So optical isomerism. Chiral carbon. It's spelt chiral, but it's pronounced chiral. All right, so it's C-H-I-R-A-L. And all a chiral carbon is a carbon atom with 4 different groups attached to it. Okay, so it's a carbon atom with 4 different groups attached to it. So I've got an example for you just here. Here, I've got a carbon atom in the middle, and then I've got different coloured spheres to show you 4 different groups. All right, and then in reality, they could be individual atoms, they could be big groups of atoms. So you could get one chiral carbon in a giant molecule. But the structural feature is it's a carbon atom with 4 different groups attached. So I'm just going to draw my tetrahedral carbon. Okay. Yeah. Okay, so there's my tetrahedral carbon. Don't forget, wedges are coming out of the board, dashes are going back into the board. All right, it's quite important when you're drawing optical isomers. And they'll have 4 different groups attached. So we'll call that A, we'll call that B, we'll call that C, and we'll call this D. All right. So why does this mean it exists as another molecule? Why is there a twin, if you like, just like with AS Isomerism, there were 2, right? So they've got the same structural formula, different arrangement of atoms in space. Well, its mirror image is crucial here, okay? Because its mirror image actually shows that the atoms are arranged slightly differently. So what I'm going to do is I'm just going to draw its mirror image, and I'm going to show you a couple of examples. So to draw its mirror image, I'm going to start with the chiral carbon again. But this time, that's sticking up still. Good. This one, which is sticking to the left, will be sticking to the right. There'll be a dash there, and there'll be a wedge. Yeah. So hopefully you can see that is the mirror image of our molecule on the left. And then I'm just going to fill in the letters where they should go. So B is at the end of the dash just there. C is that. D is over this side, and then A is still in the same position. Now, to the untrained eye, and you're quite right for thinking this, well, not right, you're incorrect, but it's understandable why you're thinking this. It looks like they're just the same molecule, but they're not, okay? So if I show you this example here, so I've got my molecule. Yep, here we go, nice, straightforward. It's got a chiral carbon with 4 different groups attached. If I bring its mirror image in, so I'm going to have to rotate this molecule around somehow. There we go. So you can clearly see, if I just hold the hydrogens at the top, the white spheres, they are the mirror images. Okay, it's a bit like your left hand and right hand. Your left hand and right hand are mirror images of one another. All right. Now, because they're mirror images, hopefully you'll appreciate that your left hand is slightly different to your right hand, and that's because they are non-superimposable. Now, what that means is if you take your left hand and right hand and then just try and put one on top of the other, you can see that the hands don't actually overlap neatly. Your thumbs are in the wrong position. If I try and do the same thing here, so these are just mirror images. Yep. If I was to just, I'm going to rotate them, and then I'm going to put one on top of the other. Yeah, and hold them in place. You can see the whites are lined up here, and at the back, the blues are lined up there. But have a look at the front. Yeah, this one's got a green pointing that way, and this one's got a red pointing that way. So just hold them up. You can see that the whites and the blues are in the same position, but the blues and the reds and the greens aren't. They're still mirror images. All I did was rotate them. Yeah, but I put one on top of the other and have all the atoms in the same space. So what you notice is they're still the same molecule, really. They've got the same structural formula. If I was writing this out, the structural formula, they'd be exactly the same, but the atoms are arranged differently in space. Yeah, so they are a form of stereo isomerism. Yep, so I'll just put one on top of the other like that. You can see blues lined up, whites lined up, but the reds and the greens are in the wrong position. Okay, so this is and we call these, a pair of optical isomers has a very special name. All right, we call them a pair of optical isomers. So this is a pair of enantiomers here. Okay, and how do I know that it exhibits optical isomerism? There is a chiral carbon, which is a carbon with 4 different groups attached to them. All right. We'll come on to why we call them optical isomers in a moment, but we need to have a bit of practice actually drawing these molecules. So let's have an example. Let's choose, I'm just going to draw a random molecule and we'll go through how to draw this mirror images. So I'll draw it out displayed. So I'll draw out displayed and I've got a new structural. Okay, so here's a molecule that I've just drawn randomly. Okay, is there a chiral carbon? Well, there should be, given the nature of this particular lesson. So you're looking for a carbon with 4 different groups attached to it. So usually we denote it with an asterisk. So I'm going to denote that as an asterisk. Okay. So there, happy days, I've got my chiral carbon. So that is my chiral carbon. Right. Now, drawing all that out in 3D displayed can be quite time consuming. You don't have to draw it displayed. All you really need to show is the 4 bonds from the tetrahedral carbon. So start off with, here's that drawing. So I'd start off with my chiral carbon and draw it tetrahedrally. Because I know a carbon with 4 groups of atoms attached to it is a tetrahedron. So I know that it must be like this. So I'm just going to start this and its mirror image. And then I'm just going to say, right, so what have I got? I'm just going to start circling the 4 different groups. So there's one, there's another, there's another, and we'll use the ring for this last bit. Yeah. And then you could literally, so you see the 4 different groups, just draw those 4 things onto the 4 points here. All right, and I'm going to do a bit of shorthand here. So the orange group is just a CH3. Okay. Now I'm going to write it as H3C because it's quite important to show the bond to the actual atom it's bonded to. All right. The purple hydrogen is pointing up. Yep. And like I say, it doesn't matter what order you put these in. Does not matter. All right. Due to rotation of these 2 single bonds here, there could be any point on that particular tetrahedron. Also, you can rotate the tetrahedron round if you like. So it does not matter. And then I'm going to do the OH here. And then this last little bit, I'm going to write as CH2 and then KUHA. Yep. And just have a look. Does that match up with what I've drawn there? Yeah, it's easy to see in display formula, but have I actually got everything? You can do an atom count if you really want to. You know, 1, 2, 3, 4, 4 carbons, how many hydrogens, and 4 carbons, sorry, and then how many hydrogens oxygens you've got. But the key thing is now, and this is probably the difficulty of this, is drawing its mirror image. So this is the left hand. We now need to draw the right hand. So let's start with the H3C here. So I know that that's going to be all the way over there as a CH3. Okay, so H3C here, CH3 there, just so you can clearly see the bond to the carbon atom, because that is a carbon-carbon bond, right? Hydrogen doesn't really matter, pointing up. Yeah, and here's where the fun begins. Because if you were to just write OH out as OH, you notice there's a bit of a problem. Yeah, there's a major flaw with drawing it like that, and this is why examiners will penalise you for this. It shows that the carbon is bonded to the hydrogen. In reality, is the carbon bonded to that hydrogen there? No, it's bonded to the oxygen. So if it's OH on the left, it must be HO on the right. Yeah. And then this bit here, again, don't write it as CH2 KUHA, because you're basically saying that this carbon here is bonded to that hydrogen, which is wrong. So you just literally have to mirror it, which is why they're mirror images. Okay, so I'm going to start with a HOOC. So KUHA becomes hook, and then H2C. Yeah, and that's why these are slightly trickier. All right, but again, when you're drawing your enantiomers, all right, in the work that your teachers have set you this week, I would go through the same procedure. I draw it out displayed, identify the chiral carbon, all right, draw out your tetrahedral structures first, fill in the 4 different groups of 1, and then carefully try and draw the mirror image. Okay, excellent. Now, obviously, in terms of nomenclature, all right, here's where you're quite fortunate, really. I don't know why the exam board don't include this, but they just don't. With EZ isomerism, which is the other form of stereoisomerism, you've got E and Z to denote between them. All right, here you would have plus and minus, all right, depending on how they affected something called plane polarized light, which I'll come on to later on. But because the naming of enantiomers is there's 2 systems you have to apply. You have to apply whether it's plus or minus, and whether it's R or S, which is 2 different ways of doing it. And just the exam board have to cut something out of the specification. In fact, they never even included it. It's not that massively difficult. But if you want to find out more, please just send me an email, and I'll gladly go through it with you. So you don't have to be able to name these as, you know, the EZs of optical isomerism. You just need to be able to draw them, all right, accurately as tetrahedrons. So we'll have one more go there. Let's try to draw a molecule, and I'll give you guys a few minutes then to have a go at drawing them, and I'll show you the answers. Let's go with, in fact, yeah, let's go with, okay. this, which is an amino acid. Okay. So again, could you turn that into a pair of enantiomers? Is there a chiral carbon anywhere? So have a go at drawing both. I'll give you about 3 or 4 minutes to have a go at that. So set out your tetrahedron, Z, plural, and then give it a go. And for a bonus point, can you name that molecule? Okay, so again, I'll get my colours out. Chiral carbon, just there. All right, and then the different groups attached. So I've got that group, I've got that group, I've got that group, and I've got that group. So again, I'm going to put them all in. Doesn't really matter what order, so I'll just put the hydrogen there. All right, I'll put the NH2 there. I'll put the Kuha there. And what's the green bit? Yeah, perfect. So again, got my chiral carbon. Like I say, I could twist the tetrahedron around. Hello, Dr. Dover. So I've got my tetrahedral carbon, and I've got the 4 different groups drawn around it. So again, you've done the basic bit. Now comes the hard part. This is where it gets really, really tricky. Errorful is what I'd say. Error streams. So let's do these top ones first. Go CH3, CH3. Again, you don't have to write it as H3C this time, as long as you are showing that the carbon is bonded to that carbon. Where students make mistakes, and these are lazy mistakes, is they'll draw it like this, which infers that the carbon is bonded to the hydrogen. So you've got to be a little bit careful when you're drawing these. Okay, make sure you're as accurate as humanly possible. And here we've got a hydrogen, which is pointing to the left, okay, which is a solid line. So it'll be that one just there. And then, again, we've got to be careful here, showing that the carbon is going to be bonded to that nitrogen. Do that first, and then what's coming off at H2, so I'll write it as H2N. So NH2 becomes H2N. And just like before, KUH on the left, when you mirror it, becomes HOOK. Yeah. And did anyone successfully name this molecule? I'm doing well getting responses out of you today, so I'm expecting there to be a blank. Oh, an answer. 2-amino-propanoic acid. Our survey says correct. Perfect. And again, like you say, if you know this now, great. If you well, it matters what good answer as well. If you don't know this yet, it does not matter because we do lots of naming practice, all the different topics of organic chemistry. So it's propanoic acid because it's that bit there, and there's an amino group, an NH2 group on the second carbon. So how would we distinguish? How would you read this in textbooks, distinguishing between them? One would be the plus isomer, all right, or as Cecil rightly says, D. So a plus isomer is the same as the D isomer, which means it rotates plane polarized light to the right or clockwise. D is for dextero, which is from the Latin for right. So ambidextrous, for example, means that you're not prevalent to any one hand. Okay. R something different dotted over. I'll come on to that in a second. This side will be minus or L. L is for Luvero, which means to the left or anti-clockwise. So again, you don't need to be able to spot because you can't really do it without a polarimeter. Great question there by Taylor. Absolutely fantastic question. Does it matter which group you attach to each branch, or is it fine as long as it's same on both enantiomers? Perfect. Yes, it is. That's an absolutely brilliant question. So again, because these single bonds are all interchangeable, they can rotate and things like that. It does not matter. Okay, if you've done the NH2 there or there or there, as long as you've mirrored it perfectly, that is fine. Okay. Yeah, well done, Cecil. So again, you'll either see it as plus or D, minus or L, and there might also be another letter at the start, either R or S. So it's technically, this molecule here could be R plus 2-aminopropanoic acid, or it could be R minus 2-aminopropanoic acid. So that's why they've not really included this nomenclature in terms of distinguishing between them. You can work these out very easily using Newman projections, but again, it's not in the specification. If you want more information about it, please feel free to send me an email and I'll go through it. So all you need to be able to do is to spot chiral carbons, draw them out, and explain how to distinguish between them. And that brings us on to our final lesson, final part of the lesson. How do I distinguish between them? I mentioned here that they rotate plane polarized light in opposite directions. But what is plane polarized light? So, first thing is we need to know what light is. Right, so GCSE physics, whilst I taught it, but back in the day, I was taught that visible light is a transverse wave. Yeah, so visible light is a transverse wave. So lights coming from the sun or from a light bulb travels up and down, up and down, up and down. However, think about it in terms of 3 dimensions. If I shine a torch at you right now, okay, some of the waves will be going up and down. So it's the old Mexican wave, isn't it? It's that one there. Yeah. So they're going up and down. But then some of them will be going from left to right, like that. Some of them will be going diagonally. All right, are all the different degrees within a circle. So if I just have a look here, right, let's put that into a bit of practice. So imagine this is a beam of light. All right, so I'm shining a torch from here over there, and now I'm going to rotate the torch at you. So here's my torch. Yep. So some of these beams, some of these waves are going up and down. Some are going left to right. Some will be going diagonally. So you can see it's basically all the degrees of a circle. That's how many waves are coming from the light source. What plane polarized light is basically you take out all these different planes, right, and you end up with just one. So this is visible light, and the waves are oscillating in all different directions. All right, so in fact, now we'll call it non-polarized light. That's non-polarized light. Polarized light is when you just get the light waves oscillating in one plane. Plane, polarized light. And how do we achieve that? How do we achieve plane polarized light? Well, you take your non-polarized light from a torch and or the sun, something like that, and you pass it through a polarimeter. And think of it as like a filter. Yeah, so a polarimeter will filter out all of these different oscillations here and leave you with the light just oscillating in one plane, up and down, up and down, up and down. Okay, so what effect then will these two molecules have on plane polarized light? Well, one of them will rotate it clockwise. So what we can do is we can take this plane polarized light. So imagine I've got my torch, I've got my polarimeter, and then I've got this plane polarized light coming up and down out of the other side. We can shine it through the sample. So let's take this one, for example. So the plane polarized light can go through the sample, and due to the way, all right, and the only reason why this happens in chiral carbons and non-chiral carbons is to do with the electron cloud around the chiral carbon itself interfering with the light wave. It will rotate it. So what you might see is, so this will be the image at the end, is that the light has been rotated. So I'll just put the normal back in. So you can see it went in, going up and down into our sample, and then afterwards it has been rotated. All right, so in this particular case, it's been rotated clockwise. And you can measure that rotation. All right, so that is an angle. All right, you use some very simple device, a polarimeter. We've actually got some at Bosworth we can show you when schools reopen. So it's being rotated. The plane polarized light has been rotated. And I'll put in this way clockwise. Yep. So that's if I shine it through this particular enantiomer. But what would happen, now this is a question, and I want someone to come up with an answer, what would happen to the plane polarized light if I didn't shine it through this enantiomer, but shone it through its mirror image? What do you think would happen? So come up with an answer, all right, and I'll draw it on there. So what would happen to plane polarized light if it was shone through the mirror image? Perfect. Well done, Kai. Yeah, it will rotate in the opposite direction. So this one rotated it clockwise. And we don't know whether that would or not. We can't do it with that experiment. I'm just using it as an example. If this one rotates it clockwise, its mirror image, its right hand, will rotate it in the opposite direction. So anti-clockwise, but also by the same degree. Yeah, so by the same degree. So imagine this angle here was 30 degrees. So this enantiomer rotated plane polarized light clockwise by 30 degrees. This one would rotate it anti-clockwise by the same amount. Yeah. And again, you don't need to be able to. So you don't need to be able to identify, because you can't do it without a polarimeter. And you don't need to worry about naming it plus D or minus L or use the RS notation I was talking about earlier. All right, that's the only way to do it. Okay, so yeah, which just answered the question there. Thank you, Cecil. That's really good. Good question, by the way, Fab. You can't tell it without actually doing an experiment. So you can't actually look at a molecule and think, right, I know that will rotate plane polarized light, okay, anti-clockwise, because you can't see the electron cloud around the actual carbon atom. Yeah, with a polarimeter, you can measure it. And this comes to our final part, right? And you've been a wonderful audience so far. Is, well, what would happen then? Because if I had a bottle of that, it would rotate it clockwise. If I had a bottle of this, it would rotate it anti-clockwise. What would happen if I had a mixture of both? Imagine I had both of these in equal amounts, equal volumes, in the same bottle. What would happen to plane polarized light? This is the final question I'm going to ask. So I've got these mixed together in a beaker. I shine plane polarized light through it. What will happen? Will it rotate clockwise? Will it rotate anti-clockwise? What do you think? Perfect, absolutely perfect. Well done, Zoe. All right, if you have an equal amount of volume, of both of these two things, there is no effect. And we call that a very specific mixture. We call it a racemic mixture, which is also called a racemate. It looks like racemate. It should be racemate. It's pronounced racemate. And what a racemate or racemic mixture is a 50-50 mix of enantiomers. Okay, so it's a 50-50 mix of enantiomers. So there is no effect on plane polarized light. So if I had a 50-50 mix of both of these, bearing in mind this is trying to rotate plane polarized light clockwise, this is trying to rotate it anti-clockwise, effectively it's a tug of war, it's a stalemate. Yeah, plane polarized light would just go straight through along the same plane. Okay. And that's pretty much it for optical isomerism. Like you say, don't worry about the notation, the nomenclature in terms of plus D, minus L, RS. Just be aware that they rotate plane polarized light in opposite directions. It's quite useful to know that because you can actually measure, because in a particular chemical reaction, it might be that you end up with you might end up with 60% of that and 40% of that. All right, you could end up with 70% of this, 30% of this. Okay, because of the stereospecificity of chemical reactions. But we'll do a bit more of that when we come on to it in our next topic. All right. Yeah, good point there. So you got no overall effect. Okay, on plane polarized light, because they're still trying to pull the light clockwise and anti-clockwise, but the net effect is no overall effect. Okay. Right. Are there any questions? And chemistry teachers in the room, have I forgotten anything?